Okay, dear students, now we're continuing with the direction coefficients of a direction on a surface. And so far, in the previous lectures, we showed that if Lm and L prime M prime, choose this pen, are direction coefficients, you must also look at your notes now, because I think since there was some problem in the pointer and this gadget that I have, this graphics tablet last time, there might be some mistakes in the lecture. So you also, I don't think there is a mistake, maybe I might have written something wrongly, so you just also check your notes. So having said that, now now I said that we had shown that if L M and L prime M prime are direction coefficients of two directions uh, at a point on the surface then we have if you have got two directions, of course that means two vectors in two directions starting from a point P on a surface. If the angle between those two directions is omega, then I think we showed that cos of omega is equal to E L prime plus F into L M prime plus L prime M plus G into M prime. I think we have done it earlier. So where EFG, of course, EFG are first order fundamental magnitudes, which are evaluated at that point on the surface, because we are talking of a surface on which there is a point and there are two different directions at that point. And if we have what we have already called the direction coefficients in those directions, so this we would get this. So that means if we let me take it a little. Okay, that means if the directions are perpendicular, it means if the directions are perpendicular, which means the angle omega is 90 degrees or pi by 2 radians, then cos of omega would be 0, which means the condition should be E L prime plus F into L M prime plus L prime M plus G M prime, this should be equal to 0. And if we take direction ratios instead of direction coefficients, then in that case the condition would become nothing much different. Lambda prime plus F times lambda mu prime plus lambda prime mu plus G into mu prime, where of course lambda mu and lambda prime mu prime are direction ratios. Now we have discussed the difference between the direction coefficients and direction ratios in those directions, the directions in question on the surface. Okay, similarly now we have certain special directions on a surface. That is the parametric curves. Now I have got something called a parametric curve at each point of a surface. So parametric curves are parametric curves are the ones which we get by putting one of the variables equal to constant, or fixing one of the two variables on the surface. The parametric curves would be of the form r is equal to r at uc, which we call a u curve, or r is equal to r cv. Now these are two parametric curves, and we know that their directions are given by the direction of v curve would be given by r sub u, and its direction would be given by its tangent vector. Of course, the, the, the direction of a curve at a point is given by its tangent. So now these are the directions of the parametric curves of two different parametric curves. But since I am interested in knowing its direction coefficients, so I have to write them as a linear combination of vectors, means the uh, basis of the tangent plane. Now that's trivially we can write it as r sub u is equal to 1 into r sub u plus 0 into r sub v, and the other parametric direction can be written as 0 into r sub u plus 1 into r sub v. Now of course, so that means the direction ratios of this are 1 0, and direction ratios of another parametric direction is 0 1, right? And if I want to evaluate the direction coefficients of these two directions, I just have to divide by the magnitude of this vector. That means, so this is basically my in place of lambda mu, and this is lambda mu for this direction, direction ratios of one parametric curve and another parametric curve. I want to evaluate, say, Lm. So that's very easy. So if I want to evaluate, so I want to evaluate, suppose this, I want to evaluate the direction coefficients of this direction. Direction ratios are already known, so I just have to divide it by its magnitude, and I have to divide it by its magnitude, and mod of Ru into 1 0 are the direction ratios of this direction r sub u, which is nothing but, which can be written as 1 by root of e 0. And similarly, direction coefficients of this direction would be 1 by norm of r sub v into 0 1, which would be the same thing as 0 1 by root of g. And you have to remember, you just have to remember this fact that E is basically r sub u dot r sub u, which is the same thing as norm of r sub u per square. And same for g. G is r sub v dot r sub v. So that's what we have used here. So that was just a simple corollary. What are the direction coefficients of these two special directions, the curves on the surface, which are of course special, because we get them by the surface itself. It is that mesh force on which the surface rests. Then there is an exercise in your notes, and that is, let me write down the exercise. I think you should do it yourself. It's very simple. Now suppose I already know the direction coefficients of a direction on a surface. I have got a surface and I know these two numbers for a surface. It's already given. Now can I find the direction coefficients of another direction which is at 90 degrees, which is perpendicular to this direction on the surface? So suppose they are L prime M prime. We can evaluate L prime M prime if Lm is given. Of course, that is the exercise in your notes. So you have to find the direction coefficients of a direction making an angle making an angle pi by 2 the direction with direction coefficients the Lm. It's a very simple exercise. You just have to solve two linear equations, then you will get the answer. So I leave it to you. It's already solved in your notes, but I expect you to do that. Try it. Now suppose now on a surface with, of course, mm, I've got two directions on a surface. So I want to find the angle between those two directions in terms of the first and second order fundamental magnitudes. So I have two directions on a surface, and of course let between them, and I want to find this expression for the angle. Now how can I evaluate the angle given 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 the point, and I from evaluating the first order fundamental magnitudes. Now what we do, we say let the coordinates of this point P are sub uv, and I represent these two directions. When I go from point, now when I want to draw a vector, I would at least need 2 points, isn't it? So suppose I've got another neighboring point. I cannot draw it exactly here. So suppose I have another neighboring point. I call it R u plus du v plus dv. So what I do, and similarly I have another point in this direction to uv. So let me call it u plus del u and v plus del v. So what does that mean? So that means I can say actually these increments in the parameters represent change in u in change in the point on the surface in two different directions. So I can think that these directions represented by, because what is changing, they are given by change in the parameter, so there would be some change in the parameter. So I can think that these two directions are given by the increments, that when we give those increments the parameter, we go in those particular directions. Okay, so that means if I want to find this vector in this direction, so I can think of it as you know this dr, this vector, this can be written as, I mean the say vector in this direction. So this can be written as of the r sub u du plus r sub d. That's what I meant, that in this tangent plane, in the tangent plane here, I am looking in directions, and since everything uh, inside this tangent plane is a linear combination of Ru and Rv, so I see what is the change in the parameters in two different directions, change in u and change in v. I just multiply by them the basis, right? Because it's like these are my x coordinate of that change, and this is my y coordinate of that change. Of course, they need not be perpendicular. We will later show that. Actually, it's given in your notes. We have a theorem that we can always choose a parameter such that Ru and Rv are mutually perpendicular. Then they would be identical with your x and y coordinates, but they need not be, and that doesn't make much of a difference. Similarly, I can think of this del r, this vector, the other direction, as, of course, my parameters in that direction to be del u del v. So it would be r sub u del u plus r sub v del v. Okay, Now it's very easy. I want to find the direction angle between these two directions. I just have to suppose psi is the angle of psi, then cos of psi would be simply dr dotted with del r divided by norm of dr multiplied by del r. And if you expand it, that means if you substitute it, so it would be down here. Okay, so what I'm writing here, let me put something under it. इसमें कुछ problem आ रही है. Okay, चलो मैं बाहर. Okay, so it would be, if you substitute the values, r sub u du plus r sub v dv dotted with, इसको पता नहीं क्या हो रहा है. Well, let me write it again. So if I substitute it here, I would get r sub u du plus r sub v dv dotted with r sub u del u plus r sub v del v whole divided by, of course, the length of r1 and length of r1. So it is dr. I can also substitute there, but you would understand. Oh shit. Okay, this is what you get. And if you expand the dot product as usual and note that r u dot